Hello, my name is Brian Fraser, and in this video I'm going to be talking about how we use C++ strings, as well as the for each loop in C++, which is in C++ 11. So, we want to talk about here what we can do with a string. We know it's a data type we can store text into, but what are the ways we can manipulate it? And then, in terms of iterating and processing the characters of a string, how can we do that better than just a for loop? We'll also see this applies to vectors as well. Okay, so what is a string? Well, the basics are a string is a class. It's a data type in C++, and it's very similar to the vector class, so kind of similar to a vector of characters. We can create a string, as shown here, with string, make it a variable named myName, and say Dr. Evil is the name. Now I can do a number of things with it. For example, I can start with getting the number of characters in the string. I can say x is equal to myname.size, where size is a member function on this object. The next thing I can do is start accessing some of the characters. So if you're familiar with array notation, which I would use in working with a vector as well, I can say here, for example, on myName, I want to access the index 4. Now, it's important to say index here because, of course, it's not the fourth character. This is actually the fifth character, which in the above string makes it the E in evil. So we pass in the index that we wish to access. Now, much like in a vector or an array, it might not check if index is valid. So using the square bracket notation, which seem to have blurred together here with this font, it might not check to see if the index is valid. It's undetermined behavior in the C++ specification as to what will happen, and so it could throw a runtime error for you, which would be nice because then you find your bug quickly, or it could simply give you some random piece of value from memory because you're simply trying to read off the end of memory. So here's an example. I create a variable named oops, and I'm going to set it to the 10th character of my name. Well, Dr. Evil is only 8 characters long, so the 10th character goes right off the end and is, who knows what, a couple characters later in memory if it's not bounds checked. If it is, I get an error immediately. If I really cared about it, I could switch over to using the at method, the member function, and that would guarantee to throw a runtime error if I tried to access something that I could not. So in many cases, using the myname sub 10 is very similar to using myname.at10. Many people will use the sub 10 because it's sort of a more traditional syntax for accessing it. Okay, so what can we do with this? Well, a fairly simple example is we create our string as before, and now I'm going to create a loop. So for I equals 0, well, I is less than the size of the string, I++, and every time through I'm going to print out not only I, but also I'll print out the name sub I. And so this is going to print out each character, printing them out vertically. So we can see the output here, starting from 0 going up to, in this case, 7, because there's 8 characters. Each time I'm printing out the character of that choice. Okay, so reading in strings, we can use cin, or in fact from any stream if you've got another stream available to you, such as an input stream. And we can just use the stream extraction, and it is overloaded to do the right thing for us. So when we stream extract into a stream, it pulls the next word in for us. Now I named my variable here word, so word is a string, but that's very specific because what's actually going on in all cases with cin here, is it's going to read until it hits white spaces. So it reads characters until it finds a white space. Now a white space is either a space, a tab, or a new line character, a line feed character effectively, which is what you get when you hit enter. So it reads until it hits some white space. It may be a space, a tab, or a new line character. So sometimes this is very desired behavior. For example, if you're reading in integers, it's nice to be able to read in them in one at a time. And in this case, with the string, you can read in single words at a time. But very often you want to read in numerous words at a time. You want to read in someone's full name from the keyboard. Or you want to read in an entire line of data from a file. So in this case, we're going to use the getLine function as shown here. So here, create a variable named full line, And then using getLine, I pass it a stream, in this case cin, and it will read an entire line of that from that stream and put that into full line until it encounters the new line character. So that's very handy if you need a full line of text. A couple other things we can do with strings. First, we can do concatenation. So plus is concatenation. And when you concatenate, you join two strings together. So concatenation is the joining of two strings. And we effectively are going to create a new string that is the concatenation of the initial two. So in fact, here I declare two strings named first and last. And then I'm going to concatenate them, but in fact I'm going to concatenate them with an additional string in the middle. So I've got three separate strings here: first, a space, and last. And I concatenate each of them together to build Dr. Evil with the space in the middle. Now again, when any time you're trying to concatenate strings, you've got to be very careful about exactly what you want between them. Do you want a comma, a space, nothing? Is there already a space? So you've got to be very conscientious of that. You can also use the plus equal operator to add to an existing string. So here's a short example. We're going to start off with a vector of strings in this case, and I'm going to set them up to the names of the Three Stooges. Now, in order for this first line to work, I have to use the compiler flag std equals C++11. This is a GCC compiler flag or G++ compiler flag to tell it that I want to use the C11 standard in terms of an initializer list. So now what I'm going to do, let's skip over a little bit for the moment, and come down here, sort of the meat of it. I want to execute this statement a number of times. I want to set all names, which is a string I've created up above, and I want to concatenate to the end of it names sub I. So in order to do that, I've got a for loop that goes for I equals 0, I less than names.size, to I plus, or for I++. So each time through the loop, I'm going to go through and I'm going to concatenate names sub I to the end of all names. And down here at the very end, I'm just going to print it out. Now that's not particularly interesting because I get Larry Curly Moe, one word, all slammed together. But I want to kind of indicate that this is a list. This might be useful, for example, in a vector printing function. Given a vector of strings, kind of show that it's a vector. So let's do that. So I'm going to start off with having all names with the open curly brace. Now each time through, I'm going to be adding to the end of this string because I've got the plus equal. I'd still get Larry Curly Moe slammed together, but then at the very end I can add in this close curly brace. So that's getting better. Now the one final thing, in order to make it look like a real vector when I print it to the screen, is I want to make it comma separated. So I don't just want to add a comma after every element, otherwise I'd have a comma after Moe. So I'm going to say only when I is greater than 0, add the comma space. And I'm doing this before I've concatenated the name. So you can imagine first time through on Larry, I don't do this, and I carry on. For Curly, Moe, and in fact any other later element that's added to the vector that when I run this code, I would add the comma space before their name. So in this case, I can actually generate a reasonably well-formed output of Larry Curly Moe all in the curly braces. Just a neat way of sort of building up the string that I'm printing to the screen. Okay, so what can I do on a string? One of the big things you might want to do is sort of check are two strings equal. This often might come up if you're trying to check a password, or you're trying to check a word in a dictionary or something like that. So I can use the double equals. This is overloaded in the string class to do the comparison of the contents of the string, to check character by character if they're the same. So here, if you're at all familiar with some movies, I can check the air shield code. I read it from the user, and if the air shield code happens to be 1, 2, 3, 4, 5, then access is granted, and you can imagine it open the air shield. So double equals compares the strings to see if they're identical content. I can also compare two strings lexicographically, which would be to say that I'm going to compare them character by character, and I want to do some sort of comparison, not just are they the same, but kind of which one is less than or greater than. So you can imagine you're trying to sort people in a long list, and two people might turn to each other and go, well, I'm Bob and you're Harry. Which one of us comes first? Okay, B comes before H, so Bob comes first. So here, you might have a your name and my name. If your name is less than my name, then you go first, else me first. Of course, in this case, what's going on is in the event of a tie, whomever is calling this out decides to go first. So, two Bobs, how does that get sorted? So, lexicographically, just to be clear, it's going to compare character by character. So you might be comparing Bob to Brian. Both start with a B. So, the first character doesn't contribute to that. Next, we go to an R for Brian and an O for Bob. So, O comes before R. So Bob, in this case, comes before Brian. So we're doing a character-by-character comparison. This is, for example, how file names are generally sorted in file browsers. Unless, of course, you're in one of the newer versions of Windows, in which case it doesn't do it just lexicographically. It also does it by the number. So if you have a number at the start of your file, it will put the 1 before the 10. Even though often 10 should lexicographically be sorted first, just because it's sort of a smarter way to go. Okay, so let's look at a bigger example here to see what's going on. What we might want to do is, given a string, we could ask the question, does this string contain a certain character? So I give you a phrase. Are there any z's in this phrase? So let's create that function. So I can have a function here that is a bool function, so it's going to ask, does it contain a character? So named containsChar. And I'm going to pass in a string and a character. Now for the moment, forget that it's a const and that we're passing it by reference. But I'm passing in just a string and a character. What do I want to do with this? Well, the easy way to make it happen is, for every character inside of my string, see if that character is the one that was given. So for I equals 0, less than size, I++. If string.I, or stub I rather, is equal to the character I passed in, then I'm going to return true. And down here, if I get through my entire string and haven't already returned, then I must know I'm false. Now this is going to be doing a case-sensitive comparison, because this comparison here, comparing two characters, if one's an uppercase A and one's a lowercase a, that's sufficient difference for them not to be the same. A couple strange things here. The first minor point is, why am I using an unsigned int? It is because the size of a string is defined to be an unsigned int. And if I just used an int, that'd be fine. It would work well in all cases before 2 billion. The issue would be that when I do this comparison, I'm able to get a warning from the compiler saying that you're doing a signed versus unsigned comparison, which can be unsafe. So I'll just get rid of that warning and put it as an unsigned int here. Now let's go back to talking about why we had this as a constant reference. So what it turns out is I can pass anything I like in as a reference, but then of course I get access to the real thing in this function. So what I'm going to do is I'm going to pass the object argument here by reference in order to avoid the expense of pass by value making a copy. So if I don't pass by reference, the default would be pass by value, and then C++ has to copy whatever the argument is such that it is available as a copy, as a duplicate, inside of my function. Now, if you're just passing in a character like the second argument here, passing a character in as a copy isn't a large expense. It can simply copy that. It makes one instruction that copies the value into the right place, and we're done. But when you've got an object, it can take a non-trivial amount of time to copy over an object. Effectively, what would happen here is it would take the string, it would have to duplicate the entire memory of the string into the argument for this function. And at the end of the function, it won't take too long to run through, it then has to get rid of that memory. So I can avoid the cost by making it a reference. And then I simply don't have to copy it. I work with the original. Now, pass by reference is in one sense dangerous because it's possible for the function to change this value, either explicitly wanting to, or maybe inadvertently through a bug. We can guard against both cases by making it a constant reference. So I make it a const, so it is not modifiable by this code, either explicitly and intentionally, or perhaps more often the case inadvertently. It just means that my code is a little bit more decoupled. I don't have to look so far to find out who changed my values. Okay, so a constant reference avoids making a copy by pass by value. So let's look at what this could look like when I call it. So down here I'm going to call cout with bool alpha just so it displays true false versus ones and zeros. And I can ask, is the character E inside hello? So I'm going to call my containsChar, pass in the string hello, and say the character E, which of course it does. So I should say true here. Does it have any lowercase a's? No, it does not. And a capital H. So here we have the output. And for all three cases that I'm testing, it gives the desired answer. So one thing I wanted to mention we saw before was that in some of these cases we're going to start to require a compiler flag. So in my project here in NetBeans, I can set a compiler flag on my project. I can right click on my project and go down to Properties. And under C++, so under the Build drop down, it may already be expanded, but I'll expand it here. Under C++, there's an area here for additional options. I'm going to need to set the -std equals C++11 compiler flag in order to use some of these features. For example, vector initialization lists, and the next thing we're going to see, which is the for each list. So I need to have this compiler flag set. So let's start seeing that. So here's the code I had before, and I can simply run it and we can see that it works. Oops. It hadn't done anything before. So I can ask it a few other things if I wanted to. Let's just prove that we're working here. Duplicate that and ask, an interesting case is a lowercase h. So, does hello contain a lowercase h? Well, it has an h, but remember that a lowercase h and an uppercase h are completely different to C++. So in this case, when I run the program, it's going to say no, h is not found in hello because, well, lowercase versus uppercase, case sensitive. Okay, so let's talk about the for each loop. So the for each loop, it's a new type of loop that's added to C++ in the C++11 spec. And what it allows us to do is it allows us to loop over all elements in a vector, generally, or you could say all elements in a supported container, where a string is actually allowable. So you can loop over not only all elements in a vector, but you could also loop over all characters in a string. Or you could loop over all elements in an array. And this, well, in one sense, didn't add anything because you could already do that. You could already say for I equals 0, I less than the size, I plus plus, give me character in the string sub I. Well, here's an example just to show you how kind of useful it can be. I've created a string. Here I'm going to set it to be nice. And now I'm going to use the for each loop. It's a little more concise. So what this means here is, for all characters ch in the variable message, I'm going to loop through. So it looks at this message and it says, okay, what characters are there in here? And at one at a time, assigns that character into ch. It then executes the body of the loop and comes back for the next character. So in this case, what I'm going to do is I'm going to call toUpper. Now, toUpper is defined to convert a character from lowercase to uppercase, so it gives me back an uppercase character all the time. And I'm going to take that, store it in as upper, and then I can simply output to the screen as upper with a dash after it. So effectively, I'm going to take some sort of message and make it look like the user's kind of yelling. So here, when I run the program, I take be nice, and I end up with be nice all in caps with a few extra dashes. Now, I totally could have written that with for I equals 0 and so forth, but there's some advantages to using this for each loop. So what are the advantages over a normal for loop? Well, the first one is that it eliminates the index variable. It eliminates the index variable. The index variable, being the I in a normal for loop, for I equals such and such, we completely get rid of that variable. And By doing so, we get rid of a big possibility of a bug. We completely get rid of the possibility of your loop going out of bounds. So this ensures your loop stays within range. Stays within the range of the values in your container, in your vector or in your string. So if you've ever had the question in your mind about, well, in this loop, do I want to go for I is less than the size or for I less than or equal to the size? Reasonably common bug, an off by one, known as a fence post error. So here it completely gets rid of that because I don't even have to write that. There's no, if you look at the definition of my for each loop, there's no I, there's no less than such and such. This is, well, for every element inside of message, do the body of this loop. Now this does require that std equals C11 or C++11 flag in order for this to work. Let's see a more complicated example. So imagine I've got a vector of doubles. I could go through them all and maybe I want to add them up. So here I can say I want to, for double cost in item costs, that's my vector up here, I want to say sum plus equals cost. So quite tight, quite concise code. Very, very easy to write and to just read through. Now this is the identical code to if I'd written it in a standard for loop. I'd have to say down here for int I equals 0, I less than item costs dot size, I plus plus. And I want to access item costs sub I and put it into the double costs. Now of course what I would normally do here is I'd inline this variable costs and I'd just have sum plus equals item costs sub I. But it's always possible to get these indices wrong. Sometimes you have to have a +1, a -1 on them, depending on how you're iterating. Again, if you can, going to this for each loop is just simpler, more straightforward. So when possible, write your loops on strings and vectors using the for each loop. So as an example sort of set of exercises you could try coding the following functions in C++. Now where you can, in a couple places you'll be able to, use a for each loop. So the first function you could try is write a function called equal. Now this would mirror the functionality of the double equal operator and just sort of show you what you have to check in order to do it. So return true if these two strings, string 1 and string 2, are character by character identical. And with this prototype, we're going to pass it in as a constant reference, each of them, so that we don't have to duplicate the objects when we call this function, which makes it faster to call. Now, if you're just calling it 5 times, no problem. But if you're doing it in the middle of the graphics loop for the next video game you're going to write, all of a sudden, these copies might begin to contribute to making the game slower. So passing the constant reference, a good idea. Next function you might want to have is reverse a string. So given any string, we generate the reverse of that string. Now it's not too hard to think about how to do this if you wanted to go through and sort of start at the end of a string and keep adding in the characters as you go. An interesting thing to think about here is how can you use the for each loop? You can do it frontwards, and every time you add a new character, you basically say, well, the string I'm building is equal to that new character plus whatever I had from before. That's a hint on that. And then finally, you can use those two functions above to create an isPalindrome function. So you simply pass it in a single character, again as a constant reference, and it can return true or false in a fairly straightforward combination of the previous two functions. So that's an exercise to try coding. Okay, so what have we seen? Well, we talked about strings. We saw how we could access them with the square bracket notation or use the at function. We talked about reading them in using stream extraction or getLine. Concatenation with plus or plus equals, and we can compare with double equals, less than or greater than. Of course, less than or equal to, greater than or equal to also work, and not equal. And then we looked at for each loops, which are a general idea that carries forward into a number of languages. They're a fantastic idea to use as much as possible. So we remove the loop index variable, and then we, for free, ensure that the loop stays within range. So that eliminates a possible source of error. Alright, well, thank you for watching.